Well, hello everybody. Welcome to Blue Marble Science. This video is going to be about the Lake Pontchartrain Causeway and measurements that prove the Earth is a sphere. Well, proves it to everybody except a guy like this guy.
Level is horizontal.
No.
Warning. Severe facial and monitor damage alert is in effect. Get out those oven mitts. Push the monitors back out of punching range. And let's light this dumpster fire and have some fun. So let's get into it. This is Lake Pontchartrain as seen from Google Earth. Now, for those of you who aren't familiar with Lake Pontchartrain, it's a rather large lake, and it's situated just north of the city of New Orleans, Louisiana. Lake Pontchartrain is unique in one respect, and that is it has a causeway crossing it. That causeway is 24 miles, or about 38.6 kilometers in length. That makes it the longest bridge in the world over water continuously. But it's absolutely straight, and that makes it one of the best places on the planet to be able to actually see the curvature of the Earth. Here's a picture of the causeway. That's taken from about the 15th story of a hotel on the south shore of the lake. You'll notice a couple of large marine spans where the elevation of the causeway rises up considerably to allow boat traffic underneath. They look extreme in this photograph because you're looking down the length of the causeway with a very long telephoto lens. And what happens is a visual effect that's called foreshortening. If you're up on top of that causeway, at the top of one of those marine spans, the view looks like this. So it's not nearly as extreme as that photograph shows. That view would be from a point about where the arrow is. But flat earthers take a look at this and they'll immediately begin with denial. They'll tell you it's refraction or it's perspective. They'll tell you it's being caused by some unknown optical effect nobody's ever heard of. Frankly, anybody that could see a moose in the road at a distance of 50 feet doesn't have any trouble seeing the curvature in that causeway. But for some reason, flat earthers do, and I think I know why. So now, let me introduce you to the two guys that originally did this work. That's Soundly on the left, and that's Jesse Kozlowski on the right. Soundly is a YouTuber, and he's probably made more video and photographs of the Pontchartrain Causeway than anybody on the planet. Jesse, meanwhile, is a professional land surveyor. Several years ago, Jesse took his GPS equipment down to New Orleans. He mounted it in his car, mounted the GPS receiver antenna on top of the car, and then drove across the causeway taking position measurements about every 10 meters. This is a GPS antenna mounted on the top of Jesse's vehicle. It's about 1.5 meters above the road surface. And there is the GPS receiver. You can see there's the height of the antenna, 1.53 meters. The distance of 10 meters is what he has selected to take his waypoints. And you see the accuracy down here. The horizontal accuracy at the moment I took this screenshot was 9 millimeters, and the vertical accuracy was 15 millimeters. That's amazingly precise compared to the accuracy we get with GPS in our telephones. But that's because Jesse is receiving constant corrections from a base station at Louisiana State University. While he was doing that, Soundly was up in the 15th floor of the Marriott Hotel there on the South Shore, videoing the causeway while Jesse was doing the measurements. Now, before we get into the actual measurements, let's take a minute and talk about GPS because that's what Jesse was using. Not the kind of GPS you and I have in our telephones, the kind of GPS that professional surveyors use. GPS is an amazing system. Our GPS receivers look for signals from the satellites, and when the receiver can see at least 4 of those satellites, by knowing the position of the satellite itself, and by measuring the length of time it takes the radio signal to travel from the satellite to the receiver, the receiver can determine exactly how far it is away from each of the satellites. Now, knowing that through a process known as trilateration, the GPS receiver can then pinpoint its location. Sounds simple, but there's a lot more to it than that. We won't go into all of those details. That's not terribly important to us for this discussion. What we want to understand is how we can use the GPS position data to reveal the shape of the causeway over Lake Pontchartrain. Now, GPS or GNSS use a coordinate system that's referred to as Earth-centered, Earth-fixed, ECEF coordinates. There's an x-axis, a y-axis, and a z-axis. The x-axis is centered on the zero meridian or the prime meridian. The y-axis is perpendicular to the x-axis. You can imagine those two axes lying along a plane that would be formed by the equator of the Earth. The z-axis passes directly through the International Reference Pole. That's essentially the geographic North and South Pole. So the origin for this coordinate system is at the center of mass of the Earth. Now, our GPS receiver determines the displacement on the x-axis, displacement on the y-axis, and the displacement on the z-axis, and that gives us an XYZ coordinate for our position. We can see the same thing in this graphic. With the x displacement, the y displacement, and the z displacement, we can then easily determine the resultant vector. Now that's going to give us our exact distance from the origin of the Earth-centered, Earth-fixed coordinate system. But it also might be the origin for a totally different coordinate system. Maybe it's a state plane system. Or maybe what we want is latitude and longitude, like our telephone tells us. Well, that's fairly easy. Angle phi is latitude, angle lambda is longitude. But there's a problem that flat earthers have here, and it's with this z-axis. This is the z-axis of the Earth-centered, Earth-fixed coordinate system. And they get that confused with this up-axis. Now that up-axis might actually be our elevation above mean sea level. Listen to this exchange.
Let's say that we got our GPS system and we put it in the XY coordinates and drove over the bridge and got a 5 point something meters all the way across.
Yeah.
Where's the curve come from?
See what I mean? Absolutely clueless.
You measure your coordinates, your XYZ coordinates, not only your elevation.
But Z is the elevation, right?
No, it's just the position.
Yeah, it is.
It's not. It's just. Yeah, it's just your position. It's not related to elevation.
It is. The Z is the elevation. That's the vertical datum. It is.
It's just your position along the vertical axis.
Yeah, the vertical datum. Yes, exactly.
So you see the problem. If you have a limited background in mathematics and geometry like this fellow, it won't be necessarily immediately obvious to you that GPS elevation data you're looking at has already considered the height of the ellipsoid and the geoid. You're effectively seeing your elevation above mean sea level. And that elevation data that looks like a z-axis to you is not the z-axis of the Earth-centered, Earth-fixed coordinate system that GPS is based on. So now let's have a look at how we could use the raw GPS XYZ data to reveal the shape of the causeway. This is just the coordinate system. We have an x-axis, a y-axis, and a z-axis. Let's put some points in space. We'll put a point there, and a point there, and a point about midway between them. Now let's draw a line. If the Earth were flat, those 3 points would lie in a straight line. Now we can take that XYZ data and we can calculate the length of the vector to each end of the causeway, and we can get a distance from the origin to the center of the causeway. Now let's toss the Earth back in here. Those two outside points are the starting point and ending point of the causeway. That line would be a chord line. The red line is the causeway itself. If the causeway is following the curvature of the Earth, that center point is going to be up here, and we'll be able to see that in the length of that vector, the distance from the center of the Earth to the center of the bridge. Now let's have a look on a flat Earth. We've got the causeway north end on the left, the causeway south end on the right. The green line is mean sea level, in other words, lake level, basically. The red line is the causeway itself, and the GPS elevation is simply the difference between mean sea level and the road surface. We can use the XYZ coordinate data to determine a distance from the origin to the north end of the causeway and a distance from the origin to the south end of the causeway. And we do the same thing for the center. But what if the Earth is spherical? Well, again, we have the north end of the causeway and the south end of it. This time we're showing the geoid. The causeway is still being represented by that red line, and our GPS elevation is simply the height above the geoid. It's still essentially elevation above mean sea level. So now the green line is the chord line, and we can get a distance from the origin to the north end of the causeway, a distance to the south end of the causeway, and on a flat Earth, that point would be in line with the north end and the south end, and our distance from the origin would look like that. But if the Earth has curvature and the causeway has curvature, the point we measure in the center of the causeway will be up there. And now we will have a distance above that chord line, which we call the sagitta. This is how we can reveal the shape of the causeway. Now this is a sample of the GPS data that was collected by Jesse. And this is out of the work that Walter Bislin did. I've just taken one small section of data so you can see what it looks like. There's a link to Walter's website right there, and I'll put it in the description too. You can look at the full data set, which contains more than 6,000 points. The point we're looking at here is point number 1660. It's on the northbound lane of the causeway. You'll also see GPS elevation data provided. You might wonder why that's even there. Well, there's a very good reason for that. That causeway has a number of those marine spans. You want to be sure that you're analyzing data that's on the level part of the causeway, not on one of those marine spans. I analyzed 3 points on each side of the causeway, one at the north end, one near the south end, and one somewhere near the middle. I'll just show you where those points were. That's the south end. You see those 2 points. There's the midpoints. And there is the north end. So let's have a look at this. If the Earth is a flat plane, the three vectors v1, v2, and v3 should form a straight line. On the other hand, if the Earth is spherical, the vectors are going to describe an arc with a radius r. Now we have the XYZ data that was collected by Jesse, and calculating the distance from the origin to the data points is very straightforward. It's simply the square root of x squared plus y squared plus z squared. You see those distances displayed there. Now let's put this on an AutoCAD drawing and see what we end up with. This is for the southbound lane, and the north end of the southbound lane is there on the left side. The origin is down here at the bottom where the red arrow is. The causeway itself is way up here at the top. In fact, at this scale, you can't even see it. Notice the dotted green line. That is the AutoCAD vector that I've drawn, and that is telling you that that's the vector I've selected to measure the length. Notice that the length is 6,372,796.257 meters. That matches our calculated distance. We do the same thing at the center and the same thing at the south end. Now let's zoom in at the top and see what that really looks like. The green line is the chord line. That would be the straight line between the north end and the south end of the causeway. The causeway is that white line. That's an arc. The green dot was the GPS XYZ position measured at about the center point of the causeway. And the sagitta is 28.1177 meters. I asked AutoCAD to tell me what the radius of that arc is, and it says 6,342,337 meters. Well, the actual value should be 6,372,817 meters, so that's about 0.5% less. But let me tell you what that actually means. If that GPS position is inaccurate by 1/10 of 1 meter, we would end up right on top of the accepted value for the radius. Let's have a look at what the northbound lane looks like. Again, the green line is the chord line and the white line is the arc. And on the northbound lane, based on the points I selected, we have a sagitta of 27.53 meters. Now that's not unexpected because the distance I used between the points on the northbound lane were closer together than the southbound lane. You would expect the sagitta to be less. The length of the arc is less. The radius in this case is very similar to what we saw on the southbound side, actually a little closer, but still about 0.5% off. And this was the data that Jesse presented. His sagitta was 28.457 meters, but he used a distance, an arc length, even longer than my southbound arc length. That's the end of that. That causeway is not flat. And you flat earthers need to stop talking about a hump of water. There's no hump of water. That causeway is following the curvature of the earth, just like the water underneath it is following the curvature of the earth. But there's something else that's pretty interesting. Now we know that the earth is an oblate spheroid. We know that it gets a little bit chubbier as we go toward the equator. That means that the south end of the causeway, that would be vector V1 for us, should actually be a little bit longer than the north end is. That's vector V2. And sure enough, we see that in the data. On the northbound side, I got a difference of 108 meters from the north to the south, and on the southbound lane, I got 109 meters. Again, the distance that I was measuring over is slightly longer on the southbound lane. Well, is that more or less what it should be? Let's find out. Here's an Earth radius by Latitude calculator. At the south end, the Earth radius should be 6,372,822 meters. On the north end, it should be 6,372,713 meters. That's a difference of 109 meters. And that's exactly what we measured. So now I want to show you some work that Walter Bislin did. Walter took Jesse's GPS data, the raw XYZ data, and generated a CAD drawing of the causeway. Watch what happens when we superimpose a picture of the causeway. That's a pretty remarkable fit, isn't it? It won't get a lot better than that. We can do one other interesting thing too, and this was always amusing to me. When flat earthers like Quantum Idiot decided that Google Earth was actually a flat model, I couldn't do anything except laugh. I know a lot of you have used Google Earth, and you've probably drawn lines on Google Earth with the measure tool. But there's a feature in there that you may not be aware of. When Google Earth comes up, it comes up with the line you're drawing clamped to the surface of the Earth. But there are alternatives. You can set it so that the line is not clamped to the Earth. It is a reference to absolute altitude, or absolute elevation if you choose. So this is what we would see in Google Earth. We would see the geoid. Now we've got a chord line, which we've been talking about, which would be a line from the north point to the south point of that bridge. But if we set the elevation just right above that chord line, we can generate a tangent line, and that way we can see the drop from horizontal. Let me show you a brief clip of me demonstrating that. I wanted to have a look at this thing in Google Earth. This is Lake Pontchartrain. You see it here. This is the north shoreline. That's the south end. I've drawn a line right down the center line of the south lane, the southbound side of the causeway. But it's not just a regular line. I'm using a Google feature that some people don't even know about. If I go to altitude, when Google comes up, it comes up clamped to the ground. Your line will be clamped to the surface of the Earth. I'm not using that. I'm using absolute. And I've got the altitude of the line set at 24 meters. I've also checked the little box that said extend the line down to the ground. Let's see what that's going to do for us. Let's go here somewhere around the middle of the causeway. I'd say it's right about in there somewhere. Then we'll just start zooming in at that point. And now you see the southbound lane and the line's running down the middle of it. And now I'm going to tilt it just a little bit so that we can see that in fact, yeah, the line is right at the surface, isn't it? Yep. Right at the surface. Very nice. Just as it should be, correct? Okay, let's see what it looks like on the end. Let's go down here to this end first. And let's tilt it a little bit. And uh-oh. What happened? It's not at the surface anymore, is it? Goodness. See if we can just scoot along. I'm sure we can do. And we see the line getting closer and closer and closer to the surface till it's right on the surface, right in there somewhere. And then as we continue down to the south end of the bridge, I have to go further than I thought. There we go. Line's starting to climb again. A little bit more, and there we go, that end. Same thing. It's like the Earth is curved, isn't it? You could try this yourself. Well, I guess that's pretty much it. I hope this brief analysis helps everyone understand how that GPS raw data can show us the shape of the planet that we live on. A huge shout out again to Soundly and Jesse and Walter for the outstanding work those guys did. It was truly a remarkable effort. And after seeing this, I wonder how the flat earthers are going to go about trying to deny it. Oh, I know. Yeah, that's how they'll do it. Hey, thanks for watching. I hope you guys enjoyed it. Don't forget those little buttons down there. Thanks to everybody that supports the channel. I couldn't do it without you. And I'll see you on the next one.